Everyone, and welcome back to Activity 29. Today we are going to finish out polar equations, talking about special types of polar curves, our rose curves, cardioids, and limacons. So these are, again, our special type of polar curve that are exhibiting unique shapes and symmetries that are special kind of to our polars as opposed to being able to be converted between both forms. The first type of polar curve is our rose curve. And these are going to be when you have a cosine n times theta, or a sine n theta. So basically it's very similar to our circle equations, except there's going to be an n value other than 1 in here, because otherwise it's going to just be a circle. So if we notice some of these different shapes, we notice that they have this flower-like picture to them, so that's why we call them rose curves. The value out front determines the length of your petal, so the a value. N, if it is also a positive integer, is going to affect the number of petals you have. If there's an even number, it's double that number of petals. If it's an odd number, it just is that number of petals. And again, we see some of those examples to the right. So for the first example, if we check out our calculators and look at these, so we would take, again, make sure we are in polar mode, but we would have 4 cosine of 2 theta. And when we graph this then, we see this shape here. And again, it's going to have symmetry officially to both the x and y axis. We know a couple of things as well, including that the what the petal length itself is. Because of that 4 out front, it's going to have a petal length of 4. And you can see that well on this picture as well, just like how far out, going out that 4 units. And in this case, there's going to be symmetry to both the x and y axis. And this is, again, an even. If we look at the next one, we notice we have an odd as our n value. We have 3 sine of 3 theta. And if we graph that, okay, notice our symmetry is going to be a little different this time. So we have, if we just are kind of rough sketching, kind of looks something like this. And what we're noticing, again, is a couple of different features. First, again, the petal length being dictated by that value out front of 3 units long. But this time we notice the symmetry is going to be to our y-axis, okay? Now that's partially due to 2 things. Number 1, that this is odd inside here, and that it's a sine. Had this been a cosine graph, notice it would have had symmetry that we could fold over to that x-axis. So the odd ones are kind of dictated by cosine versus sine. Again, that's because odd n, and it's a sine. All right, our last one, negative cosine of 4 theta. If we type this in, negative 6 cosine of 4 theta. Notice our petal length is double that, and our petals, period, are double that. We have 8, and their length on each of them is that value out front, which is 6. So we see on this one, kind of a lot happening. Let's go blue this time. And we have kind of the 1, 2, 3, 4, 5, 6, 7, and 8, right? So again, petal length on this would be 6. And then we would have symmetry on this one to both axes again. And again, that's with that even nature. So it didn't really matter if it was a cosine or a sine because we have symmetry to both the y-axis and the x-axis this time. Our next shape is going to be a cardioid. And what happens with a cardioid, it is either a, and then either a plus sign or a minus sign, and then a cosine, or the exact same thing with a sine. And the big key here is this a and this b value are both the exact same. So that's why we say a and a for these. So basically, if they match here, because sometimes you see that called a b value, then it's going to be a cardioid, which has this heart shape. So I always like to say you have the perfect match. You are the exact same. so that's why it's a cardioid. So again, you're going to see different types of symmetry. If this is a cosine graph, you would see symmetry to your x-axis, so here and here with the cosines, versus if it's a sine, you would see this symmetry to the y-axis. Now notice on these, there's that sharp point kind of at the origin each time, and again, they look like a heart. So we can graph, speaking of talking about like graphs, some of these examples. Now, reminder with your graph, okay, you want to use some exact values from this. So we have 2 plus 2 cosine of theta this time. And again, you want to make sure your table is set up, starting at 0, going up by 15 degrees for our current graph. So we can see the graph, okay, that we have that symmetric to the x-axis and fun stuff like that, but we also want to be able to graph this, right? So we would have these points here at 4, 3.9, 3.7. So if we start graphing this 4, 3.9, 3.7, 3.4, and then 3 at 60 degrees, 2.5, and then 2. And then we keep going down at 9, and then we have 1.4, 1.5, down to that, till we get to the 0. And then if you keep scrolling down, if we finish this out all the way around, we keep going, and we have back to 0, and then we're out a little bit more, out kind of with each of these plotted points to here, and then we get a little bit bigger beyond that until we are back to our exact point. So we see that. So when you're in charge of graphing like this, again, you want to use this table of values to get your exact points all the way around to make sure that this is as accurate a graph as possible. We also, again, can look at the second example. If we have 3 minus 3 sine, again, those match, so we know it's a cardioid. And again, this time, though, we're going to have symmetry to that y-axis. So again, you want to look at this table of values, again, starting at 0, ideally. So we're at 3, and then 2.2. And this one's sharper, quicker, 1.5, 8.7, and then we kind of cut in, and then we go out as we start moving around, 0.1, 0.5, out here, and then if we get to 180, we are back out to 3 on that. So we get that. Again, that heart shape, and then we keep moving around to plot each of these pieces so accurately as possible. So 3.8, 4.55, out to 5, and then I'm moving all the way down so that once we get to 270, we're down at 6. And again, we have these actual points being plotted, and then 5.8, 5.5, 5.1, and then all the way around 4.5, 3.7, back to 3. So again, actually plotting those exact points. Now our last shape is a limacon. And this is where we have A and B values where they do not necessarily equal each other, okay? So again, very similar format with that cardioid, but they are not the exact same. So we could see on some of these examples that different shapes here. Some sort of look like a cardioid, but again, these are not the exact same. So it's actually just called a dimpled limacon. We have a loop-de-loop limacon if your B value is less than your A value. And then we also have these convex ones that almost kind of have a circular shape, but they kind of flatten out there. So if we see some of these examples. So for the first one, we have 1 plus the cosine, 2 cosine of theta. So again, these are not the same, and we see that looped nature of this. So just a quick sketch here, you would have this looped nature on the inside, and it kind of goes around. 2 plus 1 cosine theta then, if we kind of flip those around, this is where we see that convex one. So instead, it's not a full circular shape, but it kind of flattens out, and then otherwise has, again, the symmetry to the x-axis for both of these. So symmetric to x, symmetric to x. And then our last one is a sine, so we know it's going to end up with symmetry to the y. If the a value is bigger than your b value, this is where you're going to have what we call a dimpled limacon, where it almost looks like a cardioid, but not quite. Like it's not quite as sharp. Instead, we call that the dimpled, and again, because of this sign, it's going to have symmetry to the y-axis. So again, we kind of see a nice little transition of all of these. Okay, this first one we can tell would be limacon because, again, these do not match, and it's one of those convex ones. Another limacon because these do not match. This one is going to be what we call the dimple because A is bigger than B, but not by much. Our next one, 1 and 1. When A equals A, this is an example of a cardioid. Have that heart shape. These, again, don't match. Back to being a limacon. This one we have the loop to it. And then our last one, this is actually just going to be going back to being our circles, right? We just talked about before. So don't forget, just because we talked about these new polar curves doesn't mean that they're always that. Circles, lines are still in play. All right, thanks everyone for watching. We'll work more in class.